Okay, now you can go ahead.
So yeah, so I'll start with the first half of the uh, Colab notebook, and yeah, let me share my screen.
Also, like, please introduce yourselves, your positions and everything.
Oh, sure. Yeah,
Yeah, thank you.
yeah, yeah. So myself, I'm Valiappan, and you must be knowing me from the other seminar and the workshop sessions, I guess. And yeah, so this tutorial is nothing but like it's trying to cover the similar topic that you similar collab notebook that you had for the workshop, but on a different data set. So here the data set, you must have seen the data set. It was just trying to segment iris and pupil from your uh, images of eyes, and you have right and left eye images, and you'll have to segment basically the iris and the pupil region from the images. So you can either do it as two separate class segmentation, where in one model you can segment the iris and one you can segment the pupil, or you can do it like multiple class segmentation, where you do segmentation of background and iris pupil separately. So that is like open for you to like explore. That's why I wanted to choose this particular data set. And yeah, I hope you guys also had a chance to download the data set and look at it. Uh, so basically, let me go over the data set once before running all the cells. Yeah. So you have training and test sets. Inside the training set, you have ground truth and images. And in order to save memory, what we have done is like we have the images of the eyes, and the ground truth will store the elliptical coordinates of the pupil and iris. So if you basically see, it'll have the same name as the images, but it'll be a CSV file. So the images will have all the PNG files, and the ground truth will have all the CSV file corresponding to all the images. Yeah. So the first thing what we would like to do is like convert all these CSV files into a mask. So that'll be the first task. So yeah, I hope you were able to run all the cells. So if you are noticing a change in the path, that's basically because I had the zip file in a different folder. So I had to push it in, I had to change the paths here. But apart from that, the rest of the code lies the same. So the first step would be to install Mona AI and then import all the necessary import functions. And then, yeah, import your drive. The next step would be to give the path corresponding to uh, the zip folder. Number three, make sure that so either decide if you want to run it in the drive, you can run it. So I didn't want to save all the images in the drive because that will be like memory consumption. So I always keep the zip folder in my drive, and whenever I want to run all these things, I move it here and unzip it in my Colab notebook. So that's why I follow this setup. But if you want to unzip it in your drive and in later on you would like to rerun them, then it's completely fine. So you just have to change your directory to your drive, give the corresponding path and unzip it there. So that will be the case. Now we'll move on to the data processing stage, where we'll take the training folder. We'll not use the testing folder right now. It is completely you can consider that to be unseen. So you'll split your training into train and validation sets here, and train your model on that, and you do all your development on the validation set, and finally you test it on your test set. So that will be completely left for your exploration, and later on while finishing the tutorial I'll let you know what is the best thing that you can achieve. So yeah, next the thing is we are going to create the mask. So change the path, so you can give the same path. So in your training set you can create another folder for mask, and in this case let me give this path. Yeah. Copy this path. And I would also simultaneously like to create the mask for the testing data as well. Okay. So these are the two functions that I would like to bring it to your notice. So basically, I use the draw ellipse function from like the ellipse function from CV2. So in that, you can actually give the coordinates of the ellipse, and you can also specify what angle the ellipse is inclined. So in this case, you can consider the ellipse is like parallel to the axis. So you don't have to confuse much. But in some cases, the eyes might be aligned or something like that. In that case, what you could do is you could give the angles here, start angle and the end angle, and it will be able to correspondingly draw the ellipse and create a mask for you. So for this dataset, you don't have to worry much about it. So these two functions will draw the ellipse and create a mask for you. So basically, it'll read the ground truth, it'll read the coordinates, it'll give that as an input to create mask, and create mask will internally call the draw ellipse function, which will draw the ellipse as a mask. So here, if you notice, thickness is 5. In that case, it will be drawing an ellipse with a thickness of 5. But in our case, we need a mask. So uh, you could specify thickness as -1. In that case, it will be a complete mask. And you could specify what should be the value of the pixels. So in our case, I would want to give the class labels as the value. So that's how you create a mask. So the rest of the values will be 0, and the corresponding coordinates will have mask as 1 or 2 based on the class label that you give. So here you will see what is the class label that I'm assigning to pupil and iris. I do see a question. Yeah. Okay, sure. You can zoom in. Is it good right now? Yeah. Okay. So let's jump into creating the mask thing. Yeah. So you could like the basic thing is like I've created a class. I don't want to create multiple functions. So what I did, I just have to give the path to the images and the ground truth, and it will basically create me a class. And I have an iterative function where if I call it based on the index, it'll read the image and the CSV. So I'll try to read the image and the corresponding CSV file, and I'll check if the file names are same or not. So as I told you, let's say for example, I would try to print and show you one of them. Maybe yeah. It might take a lot of time. So for example, like yeah, so it's 00985 underscore left dot CSV. So the same image will also be there 00985 underscore left dot PNG. So we'll just try to identify the same PNG and the corresponding CSV files. And if it is not the same, then there'll be an assertion error that will be like throwing. That's why I have this particular thing. And the next step is to like create the image. Uh, so in some cases, some of the models that you're training with segment, some of the segmentation model will take 224 cross 224 as the input. There might be some other backbone which might not have 222 cross 222 as the input size. In that case, I've given a flexibility for you to create input image and the output image. So here I've given 160 cross 224, but based on the backbones that you're using, you have the flexibility to create 224 cross 224. So this is also completely left for your exploration. I would like for you to like explore this particular part of it. So what this does is like, let's say you want 224 cross 224 images. It will basically create a mask and the image in the corresponding size. That's why I have this particular function. Let me see. I have one more question. In self, I need to change global. Yes, that's right. So in self-I, instead of glob.glob, you might have to change it to glob. Or in your import function, you could also change. Mm, so I just noticed today morning. So either you can import directly glob and do glob.glob, or you can import from glob, import glob. So that's the only thing. Yeah. Thanks for noticing that. Yeah. So now we could just create the complete mask sphere. So coming back again. So the thing is, it'll create the image in the particular size that you're asking for. So the actual image, input image, is of the size 120, 160 cross 224. But based on the backbone, I might want to add some more pixels. Like for example, if the image of the size 160 cross 224 and I want 224 cross 224, I'll patch black image. I'll patch zeros and make it 224 cross 224. Uh, so this is that particular step, and then I'll read the CSV, get the coordinates, and create the pupil and iris mask. So it will call the create mask function internally, and yes, that'll create the mask. Finally, I'll save that as pupil and iris mask. And there is also one more image which will like concatenate all the functions. So this local is nothing but it will have like multiple access. But at this point, I didn't want to have multiple channels. So in some cases, let's say you want to like have multiple channels for like each one of the segments, you could also do that. So at this point, this might be not useful. But let's say you want to have two models. One model will predict the pupil and the other model will predict the iris. You could also use this as well. But as of now, I'm just returning the pupil mask and the iris mask, the corresponding image name, so that I could save the mask together in the same image name. That's why I'm passing this. This is the resized image. Based on whatever size you're giving, it'll accordingly resize it for you. Here, I'm not resizing it. I'm just giving the default values. So we can stick to that right now. But based on your backbone, you might have to think about it. So yeah. So far, I think I'm clear. In case if you're not understanding any backbone, or what I mean by backbone, you can also ask that. Yeah. Could you please comment about the choice of number of channels? Yeah. So yeah, I was also trying to experiment with dataset where I wanted to have a pupil in one particular channel. So although it'll be like you can have both of them in the same channel, given that you have 0 to 255 pixels, you can label each one of the pixel corresponding to the class that it represents. So for example, pupil can represent class 0. Sorry, background can represent class 0, pupil can be 1, and iris can be 2. But I was also trying to experiment with trying to have multiple channels where I take one particular channel for pupil and one particular channel for iris. But that was a different experiment uh, where I could like train multiple things and have a separate loss function and see if it was improving segmentation thing. But at this point, it might be a little confusing. But yeah, you can just avoid that right now. Yeah. So here I'm giving the size as 224 cross 224, but I'm letting you explore different sizes as well. Yeah. So this might take some time, but it should create the mask. Meanwhile, I might also have to change the paths. Yeah. And the way that I've created this collab notebook is not very clean. It should take all the paths directly. I am hard coding all the paths, so please pardon me for this. This is training. Okay, I think this should be good. I didn't. and you don't have to worry about changing the paths. I'll make sure to give the same Colab notebook again so that you don't have to worry about it. So in my case, I am transferring all the images to the Colab notebooks files. Uh, if you're running it in your drive, in the folder MacMed hacks or something like that, then there won't be any change to the path. So I think it should be clear path. So yeah. So let's see one of the masks, but maybe I think it might not be visible because the pixel values will be 1 and 2. Uh, but in the exploratory data analysis, you might be able to see all the differences completely. In the meanwhile, let's run the test mask. As I said, I'm gonna change the paths here. I'm extremely sorry. Okay, looks good. Okay, so here I give the root directory where for all the training and the development will come from the training set. The testing will be untouched. So uh, based on what you've learned so far, I would let you to explore about how to use the testing set separately. Okay, I think it's glob. As one of our friends pointed out, it's glob, not glob.glob, it's glob. Yeah, should be fine, I think. Yeah, so it's picking up, for example, if you see, it's picking up one ground truth, it's picking up the images, I think. Yeah, from the mask and the corresponding images. Let's run rest of them. There should be any problem with the path, I guess. Okay, yeah. So here, if you see, these first 5 numbers corresponds to the patient, and the left and the right corresponds to which eyes, left or the right eye. So we have 748 patients. Yeah, okay. Let's observe the mask. So here, in this case, if you see the mask, the dimension, the image is 160 cross 224. But in order to use the general backbones that we have, 224 cross 224 is the image. So I'm just padding zeros to make it 224 cross 224. Let's observe how the image would look like. Yeah. Yeah. So it's a 160 cross 160 image, but we have padded zeros and then created a mask. So that's how it looks like. And to just confirm, you can make sure that if it is drawing the pupil and iris correctly or not. So that's how it works. Yeah. So far, I think it's good. Do you have any questions? The rest of the process is very simple. We do the same thing. We'll try to find out what is the mask area, but here we'll do something different. We'll try to find out what is the pupil and iris area also, and that we'll use that for exploration. I think I also didn't mention one more thing. So if you see here, iris is coded differently, pupil is coded differently. Did I swap that? Sorry. The yellow one is pupil and the green one is iris. Yeah. So how do you think that difference came up? So basically, while creating the images, what I did, before saving it, I made sure that I multiplied 2 with the pupil mask and 1 with the iris mask. So in that way, you will have, so basically the mask that comes out of the create mask function will have the values, every pixel's value will be 1. But in order to have the differentiation between the classes, I'm trying to multiply 2 with that. 2 with the pupil mask, and as it is, I'm leaving the iris. So what do you think will be the class label of pupil and iris? So basically what happens is like pupil and iris are actually one inside the other, right? So pupil is inside. So it'll also be highlighted. So iris will have a bigger circle. I'll show you in the image. So iris is the bigger circle. So all the pixels inside this bigger circle will be 1, and you're multiplying 2 with pupil. So basically what happens is iris will have 1 and pupil will have 3 as the class label. Uh, so finally, when you're trying to separate the mask out, you have to find out where all the pixels are 3 that corresponds to pupil, and where all the uh, pixel values are 1 that corresponds to iris. So this was clear, I guess. If there is any doubt, please like point out in the chat. I will be able to explain it again to you. But most of the thing is done. Yeah, so that's where right now we are, and we'll try to find out what are all the unique masks that's available. Yeah, it's 0 for the background, 1 for the iris, and 3 for the pupil. You don't have to multiply 2 with the pupil. You can still, as it is, leave the pupil and add it up. Then it will be 0, 1, and 2. So just to differentiate it and show, I made sure to multiply that by 2 so that you'll understand. But apart from that, nothing different. You can just simply add the images. I see a question. Yeah, that's what I said. I wanted to differentiate it and show it to you. That's why I made sure I multiplied by 2 so that I can show you like 0, 1, and 3. But you can directly add them up. Still, pupil will have 2 because it's having an overlapping area with iris. So wherever the iris is there, there will be pupil. Wherever iris is there will be 1, and pupil will also have 1. So when you add both the images, pupil will by default have pixels as 2. So I just want to differentiate it by multiplying 2 with the pupil pixels. So here you see 3 for all the pupils and 1 for all the iris. But I can assure you that you can just directly add them up. Still, it will be the unique pixels will be 0, 1, and 2. Once everything is done, I can again rerun it and show you without multiplying 2. So, or I will leave it as an experiment for you so that you can experiment and see. But nothing, it won't make any difference. It could still be pupil plus iris as a mask, and it will still work fine. It won't throw an error. I just wanted to show you how you can differentiate and create class labels. That's it. So here the case is where iris is overlapping with pupil. Imagine a case where your iris and pupil, two different segments are not overlapping. In that case, to differentiate, if both the pixels are 1 and 1, you have to do some kind of a multiplication. So imagine as if in those cases, you might have to do these kind of things to make your pixels differentiated. So that's one thing that I wanted to point it out. Apart from that, nothing different. Let's read the images. And let's see if is there any difference in the pixels, or is it all fine? Is it all having the same dimensions? Yeah, it should be the same. Yeah, 224 cross 224. Okay. So here I would like to understand what is the total area, the iris area, and the pupil area. So for the area, we are just counting all the pixels together, and here you go. So if the mask value is equal to 1, we sum that up all. So here it will be like sum of all the iris area, sum of all the pupil areas, and the total area. This is very similar to what we did during the workshop, and I'm trying to plot the histogram here with only the total area. Let's see how it looks like. This data set is a very small data set. I made sure like you all guys should be able to run during the tutorial. That's why it's a very small. But as you go for a bigger data set, I guess you will see a very good uh, bell-shaped curve. You won't see gaps like this. You will be able to find out. You will be able to have a good curve. Uh, this is the iris area, which looks much better, and the mean lies around 150 pixels or once. Sorry, 1500 and 1600. And this is the pupil area. Pupil is almost very small, so you can see that it covers only 200 to 300 pixels on an average. Yeah, this is very. This is where we create the mask area bin, and now we split it into uh, train and test. But of course, like here, the test is like we are splitting the portion of your training set as a test in order to check how it is working. But the actual test set is still untouched. So once you develop your model using this split, you can test it on your test set and see how well it is working. That's it. So let's create the split. Yeah, and I guess this is all the same steps that you have done during the workshop. Nothing different. Let's observe how is your test and train. Is the distribution different? So why do we check the distribution? In order like, so your training and the test should have a similar distribution. If it is far apart, if the means lie different, what happens is you're trying to learn something from a certain distribution, and when the test set is on a different distribution, then it might not be able to guess or predict for the corresponding data sets. And that's why you always check what is your distribution of test and train. So here we have three labels. One is the background, one is the pupil, and the iris. So we'll not be using the background pixels or the background area. We'll be more concentrating on the total area, and then pupil and iris. That's it. So you could see the distribution here. Yeah. It's almost overlapping, so nothing bad. Yeah, you see a question. Training has higher density than test set. Can you density with the total area? What do you mean by no? Wait. Which graph is it? Okay, it's a total area, I guess. You mean okay. So you mean at 2000 there's like a lot of so density will basically like yeah, uh, basically represent the count. So it says that it has so many images in the training set. So for you can take it as if there are 100 images which has total area as 2000. But in the case of test, the number of density that is there is less. So if training has less density of images in that particular area, then it might cause an issue because for that particular total area, for example, 3000, if you see, test has more density than train. So in that case, it might be the case where it has less samples in your training set as a data set, and it might not be able to generalize well for total area of 300. Well spotted. Yes. So whenever if your training density is less than the test, then there's a case where mm, it doesn't have a lot of samples for it to generalize. So that might be the case. So if your test density is lesser than the train density, it's okay. You have more samples on the training for you to learn. So that should not be a problem. Yeah. No problem. Yeah. So far it's good. So we have done all the data visualization. We've tried understanding. Now it comes to the part where you have to resize the images correspondingly and try to train the model based on the backbone. So here, trying to achieve good results depends upon what kind of a model you use, what kind of backbones you use, what pre-processing and post-processing steps that you do. So I will leave it to Hussein to continue from this point. And if there is any doubt, you could also post it on the chat. I'll try to answer from there. Does that does that sound good?
Thank you, Ali, for your great explanation. Okay, let me share my screen. Do you have my screen? I have to spot all of these. Okay, do you have my screen now?
I can't see a screen right now.
You can see.
I can't see.
Oh, let me stop and share it again.
Now we can see. Yeah, it's good. It's good.
Yeah. Unfortunately, I ran out of GPU limitation. I was busy changing my account and running it again. Hopefully, it's fine now.
Yeah.
Okay. So thank you, Alima, for covering the data pre-processing step.
Mhm.
Now, next step is applying transformations. To just simply say why we need transformation. Just before that first question, how much are you familiar with training a pipeline? Have you seen that in previous lectures? Question also, can you guide me how much I should go in detail? Have you seen a training pipeline in previous sessions? That would be great if you can give me some feedbacks. Okay, can you hear me?
Yes, yes.
Okay.
Yeah.
So I'll try to explain like briefly, and if you needed like more information, more detail, let me know. So why we need transformations? Firstly, we need some transformation as part of pre-processing. So we want to maybe apply some steps always before moving to training in order to prepare our data set. For example, we want to move all images to a fixed size, and all of them should have a fixed size because we want to design our architecture based on that size. So that can be some part of transformation that we might do. For example, here we define a target size that we want to move our data to this size always. And also some other transformation we might need is like moving to tensor or doing normalization based on mean, STD, or any other approach that we have. So after having some transformation, I will explain this. Firstly, here we are working with Monai. Monai is a library on top of PyTorch. So it extends PyTorch and it uses PyTorch. It's very similar to PyTorch, and it's a good library for working with deep learning models, especially in medical domain. I haven't used it before. I usually use Torch Fusion or augmentation for transformations, but it's a good library. I wanted to also learn it, so I started working with that. So in Monai, we have an option so MN. I define Monai as MN. So in the dataset, we have a option here, persistent dataset. So when we create our dataset with using this class, we can pass our transformation to this. So each time I'm getting each item from this class, automatically this transformation will be applied to our data each time I'm calling. So if I call, let's say, one sample several times, each time I'm applying the transformation to that image. So if I have some random transformation in my pipeline, we might have different variability in our image. And a good thing about this is that, and good thing about this option in Monai is that when we have, like here, when we have some, in my pipeline now, I have some transformations that I want to always apply. And I have some random transformations based on a probability. For example, let's say apply this transformation with this probability. So 50% of times it will be applied, not always. So when I use this class, this option, it creates a data set for me. And here I define a cache. So this one is just for clear all the cache I had before. And then I define a path for the cache. I want to keep my cache there. So what it does is that it firstly gonna start working, like applying these transformations, and it's gonna apply first all these these functions that will be always applied and keep them somewhere. So next time when I'm applying the transformation pipeline, because I know that I'm going to always apply these, so I don't have to like each time get image, apply these, and go to the random transformation. I can one time just apply all these lines that I want to always apply, keep like cache them, and next time I just read them and only apply these random transformations. So that would be much more efficient and faster. So do this because of this in training process, maybe in first part, you see that it's slower applying transformation because it's applying all of them, then cache them. But in next iterations, it would be much faster. Yeah, my question was, how much are you familiar with implementing a training process or transformations? I wanted to know how much I should go in detail. So let's take a look at these different transformations. So the first one is to load the image and mask. So I want to always load it. And here I applied this transformation only on mask. And what I'm doing is say where in the mask where the value is bigger than 2, make it 2. Why I'm doing this? Because as Valerian said, in our data set, we have label 1 for iris and label 3 for pupil. But that causes issue when you want to use one-hot encoding in MONAI, because it expects value be like consistent. For example, when I say the output channel is 3, it expects me to have values like 0, 1, 2. So this is something that I need to do here as part of preprocessing. So I changed the value, I changed 3s to 2s. So now my unique value would be 0 for background, 1 for iris, and 2 for pupil. And this is just for making sure that the first channel is, the first index is channels, because in image, usually when you load image and when we are working with images, we have firstly a spatial dimension. So it would be width, height, and then channels. But when we want to work with tensors and totally working deep learning, we have channels, then width and height. So we need to move channels to the first index always. And this is just for a rotating 90 degree. So changing like rows and columns. And because when we load image, that's a feature of MONAI, I think it's rotated 90 degree automatically. So I want to get it back. And here we have some random transformations. You can check all these options or all the functions from MONAI documentation. Yeah. So you can search it, see what's the parameters, how it works. It shouldn't be difficult. And why we need random transformation, maybe we call it augmentation. The reason is first, avoiding overfitting. Why overfitting? Because let's say we have some images and during training process, our model is training to learn some features to finally do the right prediction. But when each time I'm passing the like exactly same information, it's gonna learn to memorize only these images, only this data. So it do anything to memorize some features to finally do the right prediction, but it doesn't guarantee that it's gonna perform well on unseen data set, like on test data set. So deep learning models can like memorize crazy thing. Let's say you want to do a car classification, and maybe it's just focus on like the driver and say, okay, when we have a driver, the class is like Porsche. Or I don't know, when we have a label inside of our image, it's like a URL. So I say based on this, okay, this is the correct label. But that doesn't make sense. We want to force the model to actually learn the patterns, not just memorizing some features from the images that can be different in different images. So I create like, we apply random transformation to add different, like to create different images, increase data variability. And so by, for example, adding rotation, like doing flip, changing the contrast, I'm creating like different images each time. And I said that we are doing this based on the probability. And each time I'm getting item from this data set, it will be applied. So during the training process, in each epoch, it's like I have many variety of images. So in one operation, in one iteration might apply this one, and next one might apply this one. So for exactly same image, we can have different variations. And surely that just take a look what's happening here. We say do the random rotation. This is for radian. It would be something around like 50 degree. So it's gonna select something between this and with 50% probability. And this bilinear and nearest is for the masks. When we are working with like masks, we want them to be exactly. So if we don't put this, we might have mixed values between like 0, 1, and it's gonna destroy the mask. So keep in mind to have this as well. And for random flip, first time I use a special axis 0. Let me check if you have any question. Okay. No worries. So firstly, we do it in x-axis, so it would be vertical. And next time I'm applying the same, but do the flip for 1, which is for height, and it would be like horizontal flip. And then we have like random adjust contrast, so changing the contrast, and random zoom for this like values portions, and again for 50% of probability. And also we have some always apply, like resizing. I want to resize it to the target size. Since our images were 20 to 24 in if I'm not wrong, 160. I want to make them a square. Usually making them a square is having a square data is better. And one reason for that is when we want to use pre-trained data. Usually pre-trained weights are like been trained on a square images. So in this case, we can use those models better. Also, we apply like a scale intensity. We click them, so we move the intensity to 0 and 1. This is because if we have like very high volume, very small ones, that cause issue. For example, for like high values, we might have gradient explosion and these issues. So we want to normalize them usually. And finally, move them to tensor. And this was for training transformation. Also, something that I didn't mention, be careful about if you want to apply in both image or mask or only image. For example, I don't want to apply like contrast on mask. There's no reason for that. Or I don't want to normalize masks. I want to keep that labels. And for test transformation, we don't need random transformations. We have the test data. We just want to do the prediction. So here, I just copied the always apply functions. So this for loading image, resizing, normalizing, and finally move them to tensor. So far, is there any question about transformation? Very good.
No questions in the chat also.
Sorry, I can hear you. Okay. So let me know if you have any questions. So we create our data set using the transformations. I use train transforms for train and test transforms for test. Okay. this is for just visualization. I create a function to just give an image and mask. I do permute. This is for, again, changing the dimension. I mentioned that, for example, if I want to use, I'm sure it expect me to pass channel at the last index, so it would be in this shape. So I do permute to like change the dimension. Just this is for visualizing images. So I get the first data, and just to see the values, yeah, now we have 0, 1, 2 as unique values. I get the first data. So when I call it like this, now I'm sure that those transformations already are applied. That's the feature of that data set. So then we pass image and mask to this for visualization, and I do this like 10 times. So since each time I'm applying the transformation and we have random transformation, we will get different results. This is due to contrast views. You can see we have, for example, vertical flip here. We have rotation, contrast. So some of them might be similar due to probability that we have, but we have different variation of images that can help us during the training process. Okay, let's move to implementing our pipeline for training and using the model. So for the model, for segmentation model, usually unit like based models is used. Still they are performing, like they are a state of art. The architecture is like the best now architecture for segmentation. The changes is like just changing the backbone, changing like the layers, sizes, or I don't know, adding some attentions, and like different options. Shortly say what is unit model, unit architecture. So it is made of like encoder part, decoder part, and what we do during encoder, we increase number of channels and we decrease image spatial dimension. We can apply like max pooling or change the stride for decreasing spatial dimension. And here we have a like middle layer that after here we go to decoder part. That's the purpose is to retrieve image to the original size, original spatial dimension that we had, and again decreasing the number of channels. So by doing this, it's like encoding something. It's coming from autoencoders and then decoding. So by doing this, we are forcing the model to actually learn some features. We are moving it to like a small dimension and then try to get it back. So during this process, the model learns to like learn these features, and we have this specific connection in the middle. That's for out. We pass output of each encoder to the decoder part, and we concat with the input of decoder. So by doing this, it helps us to like move some low-level features, and still we have high-level features here. And by doing this, still we can preserve those low-level features. Okay, we're here. So I use Monai for the architecture. It's like flexible units. It's very similar to unit. And the input channel is 3 because we are working with RGB images. the output channel, we should be careful that is 3 here because we want to predict 3 classes: background, iris, or pupil. And I use efficient V0 for background. It's very lightweight model, and we use pre-training also. This line of code is to get access to CUDA is available. So now device would be CUDA, and I move the model to CUDA, which is GPU for when we want to use GPU. And I train my model for 20 epochs with this learning rate and backslides. You can try different combinations. And here we create data loaders based on those datasets that we created for train and test. And what data loader do is to just based on the batch size, each time it's gonna divide this dataset to different batches, keep them somewhere, and during the training process, each time it's gonna load one of those batch of data. And we could shuffle through because we want to do shuffling during the training. So we don't want to have a same order each time. It's good to have shuffling. We don't want that in test set because there's no reason for that. And for loss function and optimizer, I use this the same we had in workshop. Usually for the loss, dice loss is very popular one when it comes to image segmentation, and also IOU, I think. So these are popular ones. It's just intersections over the union. So if we predicted 100% correctly, intersection would be exactly like union, right? So we get 1 for the dice, or 100% for dice. And for optimizer, we use Adam. Adam is a very famous one. So loss, always we want to okay. Thank you, Arifan. We always need a loss function to calculate the loss. Now we need the optimizer to, based on the loss that we have, we want to update our parameters. So we usually calculate gradients, and based on some approaches, we update our parameters based on those calculated gradients. So if you it's good to learn about what different options we have, what SGB, and what's different with other. So we don't have time now, but it's good to search them and learn them. And this is for evaluation function. Again, we use dice metric. This loss function is combined not only with dice, also with cross entropy. So this is sum of dice and cross entropy. Cross entropy is another loss that says, for example, it's made of, the formula is made of logarithms. So it says, for example, if here is, we have true positive, if we correctly predicted, okay, it's gonna, we get a better result. If we predict it wrong, also for false negative, we have a penalty. Yes, we haven't put this in your notebook. The point was that you define this, so this was part of the assignment, but we will upload the answers, the solutions, so you will have it. Okay, for evaluation, we just only use the dice metric. And why we here put to 1 hot encoding true is that using this function of Monai, it automatically has this feature to like do the prediction using one-hot encoding. If you don't know what is one-hot encoding, it's very simple. So when we have different values for label, like 0, 1, 2, what one-hot encoding, we can also show you here, for example, like this one. So if we have one, like 3 values, we create like 3 channels, and each of them focus on one of these features. For example, for instead of let's say 1, 2, 3, we say okay, we have like a channel for background. If it is background, we say it is 1, otherwise it's 0. If it is like iris, it is 1, otherwise it's 0 in this channel. And also for people. So we will have like 3 channels, and each channel is binary channels that shows which if the value represent that class or not. The choice of backbone, firstly depends on your probably your task, your data set, and many other things that we need to consider. But efficient 0 is very like simple and efficient one. So if we use like heavier models with larger parameters, we might get better results because we are doing convolution in this many layer of convolution during these backbones. So this backbone is like for encoder and decoder part that we mentioned in the unit architecture. For example, here, each of these blocks are exactly like those backbones that we are using. That can be like a block of efficientness or resonance or complex, many other architecture that we have. So some convolutions happening during these blocks. So if we increase them, change the architecture, of course, we might get like different results. It's still the shape is unit, but each of these blocks and what's happening inside them can be different. Does that answer your question? Okay. So, okay, let's go to training process. Probably you've seen the training process a lot. Just to briefly explain it, we repeat this process for number of epochs that we have. And each time we have like a training loop, what we do is to, for like we load each time a batch from the data loader we had. And this taqaddum or TQDM is for like showing the progress bar during the process. So we load images, move them to the device, which is now CUDA, the GPU. And this is for making like every gradient that we have, make them 0. Firstly, we do it, make them 0, then calculate them, update it, and make them 0 again. So we don't want to affect to the next epochs, next iterations. And we predict, so we pass the images to the model to predict the result. From the loss function we have, we compare the mask with our predictions, and this is gonna out, since we had one-hot encoding true, it's gonna firstly convert masks which were binary to 3 channels for different classes, then compare this with our predictions, because in predictions we had, if you remember, we had 3 channels. So we should apply one-hot encoding on the mask and then calculate the loss. Otherwise, you will get error. So be careful about it when we want to do multi-class segmentations. Yeah, we should pay more attention to this part. And then based on the loss calculated, we do backward during back. So when I say dot backward, it's going to calculate gradients for all the parameters. do the backpropagation, and based on the calculated gradient, when I use optimizer.step, say, okay, from the optimizer that we use, based on the gradients, the loss we calculated, go and update parameters in order to reduce this loss. And here is just for keeping the loss. And finally, we apply softmax on dimension 1, which is our channels. So we said that we have 3 channels. We want to apply the softmax on each channel. And finally, we have a probability for under like each channel. And then we get the argmax. This is for predicting a mask. So in segmentation, we want to do like a pixel-wise classification. And so I want for each pixel have like 0, 1, if it's in like class. In ideal, like when we have multi-class, it would be like 0, 1, 2, 3, 0, 1, 2. But now we have different channels and each of them are binary. We go just with 0, 1 per each channel. So if it's not, for example, pupil 0, it is 1. And then, so by doing this, I'm converting probabilities to masks actually. So now I can compare them with the real mask that we had and calculate the dice. So this is for evaluation. And these are just for keeping the loss and keeping the dices. So later on we can plot them. And this is the validation loop. So after each time of training, we do the validation. And something that we need to be careful is exactly this part. When I want to do training, I change the mode to .train. And when we want to do validation or test, we change mode to eval mode. And what's happening by doing this is that when we go to eval mode, we are like we are ignoring some layers that we only wanted to use during the training process. For example, if you know about dropouts, which is like applied to avoid overfitting during the training process. So when I use the eval mode, it's gonna automatically ignore those dropouts layers. So always keep in mind to change the mode. So for validation, we get the data from tests. And this is not exactly like our test set. We have 2 folders, train set and test set. We just loaded train set. So all the data we have now is train set. But using crossfold, we separated 1 fold for testing. So this is actually like a validation that we are doing. It's not exactly our test set. This test deal data loader is for validation. And this is, we do validation during the training process to tune the hyperparameters. So by doing this, I have an idea of when to stop it, when it's enough, because we cannot decide on training data, on a training result, because we said that it's going to memorize, it's seeing the data, it's going to memorize it. And each time it's getting better and better, and it's overfitting. It doesn't guarantee that it's going to perform better on unseen data. But we don't update like our parameters based on validation set. So we keep this validation set to have a like a estimation how our result how our hyperparameters are good and when we should stop. And if we want to like decide change hyperparameters, we can use this validation. And then now we have a model that is trained. Now we go to apply it on the test set, which is totally unseen. I repeat again, validation is not totally unseen because we are saving the best model regarding the validation loss. So still our final model is dependent to this validation set. Is it clear? Okay, so here we use also the torch node graph because we don't want to calculate gradients in validation because we don't want to update our parameters during validation process. We do prediction and then calculate like the dice for validation. And finally, during each epoch, we check that if the new validation loss is less, save this model. So we want to save always the best model based on that. What is the result on validation set? And also, I use like an earliest stopping method here. What is earliest stopping? We can like it's like one method that help us to stop the training process. So we can define like a value, a number, let's say 3, and say after like 3 epoch, if we didn't get like if the validation loss didn't decrease, stop the training. So it's like one way to do it more efficient. So maybe like epoch 10, we don't get any better results and the validation loss is not getting better. We just are overfitting to the train set. So I don't need to keep going. I can save the GPU memory and just stop it somewhere. So I say that if validation is like higher than best validation, increase patient. So this is like a variable, I increase it. And then say if this patient is greater or equal to that earliest stopping, let's say 3, then break this pipeline, this process. So let's see the results. Starting from epoch 1 here. Okay. Now we calculated the dice for different classes that we have. So this is the dice for train set, and the first parameter is the dice for background. So if we correctly predicted the background, and then this is for iris, and this is for pupil. And also we have it for validation. Validation is better. We can see here. The reason is that one time we trained it on the train set and then move to the validation. So it should usually perform better. And okay, saving the model. If we can see something here that's at the first epochs, the result for pupil is very bad. And it's still very bad. But here we have a jump from epoch 4. The reason is that the reason can be like because of initialization of like weights biases, and since people are very like a small area, it's harder to find it. So we expect to like have not a like good result as good as like iris, because it's larger, it's easier to identify, but for people it's harder to find. But here, so from here, the model is somehow learning, okay, where is it? It's getting better and better. So it takes time to the model learn. And I applied it for like 20 bucks. And finally, we have like, we expect, okay, to have a better result for background. And this is for iris. And finally for people, if you keep going, still you might get even better results. So then we plot loss and the dice. We calculate it there. So here we can see the good pattern, it's decreasing for both. And we can see that for validation, we have like a smaller loss. We said because we are doing we are calculating validation after the training. So during the training, it's learning some, it's updating some parameters, then we are applying validation. Well, it's not this. And for the dice, you can see that it's increasing for both training and validation. So this shows that even if we continue, we might get better results. And finally, that we have the model. We train it based on the train set and validation set. Now we had a test data in our data set. Now we can load it here. So firstly, what I do, I save the best model in here. I save the best model. I keep like the parameter of this model and save it somewhere. So next time I want to load it, firstly, I should use the exact same architecture because our parameters are based on the sizes and the architecture that we have. So I use exactly the model which is defined previously. If it's not, we should exactly copy the architecture we have here and then load the dictionary. So I'm creating the model and updating parameters based on the parameter that we saved. And keep in mind that every time it's good to save it and then load it and then test it, because you might find the best model in like epoch 10, but you keep going the training process, and in epoch 100 you have like an overfitted model. You don't want to use that model. You want to use the best model that you save for testing. So first we load it and then start testing. And here is just for, again, I copied the above cell for loading the test data set, creating test data loader. So it's not very efficient and clean code. You can have like a class or some functions for passing just like a data frame and get the result. You can code it better, of course. And this is for, so it's very similar to the validation. We just load the data, do the prediction. You don't need this line. And then calculate loss, calculate the dice, and just print it. I think I cannot run this load since my runtime killed. But yeah, if you run it, I got something like 90, you know, very like close to this result for the testing. So is there any question? If any part is confusing, if you need more explanation, just let me know. So we will upload also the solution for you. Try to work on it. It's good to understand what the general pipeline, what's happening, and so it will be similar each time. But also we will have some detail. You might get like errors because of that we have multi-class. You need to do 100 encoding. You might have these issues, so make sure that you run it by yourself and fix those issues. Okay. If there is no question, thank you everyone.
Yeah, thank you so much, Hussein.
Yeah, sorry that it took a while.
No, it's all okay. It's always the case with tutorials. They're always
Okay.
so I'm gonna stop recording.